Hi, welcome back to this class. Transformer Encoder. This is part 5. We have earlier 4 parts. We explained them. Um, the first part, just to recall what we had done, we explained encoder in brief with decoder in brief all together. And in part 2, we explained positional embedding um, with input embedding. In part 3, we talked about multi-head attention in detail for a sentence, uh, I like Rojava. And then in part 4, we explained both add residual and normalization layer. And in part um, in this part, we talk about feed forward. So in this part, we talk about feed forward neural network. So here is the feed forward network. So let's go and explain it in detail. So recall for what we had done in earlier layer, it was layer add and normalization, and we received this input, which is residual. That's 3 by 4 for I like Rojava. So the first row is I, second row is like, and the third row is Rojava. Okay, so now we are trying to do structure of feed-forward network, um, which is applied independent to each token. So each token, each word, they need feed-forward. So that's the formula for feed-forward. Here, reload activation function, the input multiplied by the weight matrix plus B1. So that would be hidden one. And if we multiply it by weight matrix um, plus B bias, then that would be second layer of hidden, second hidden layer. So assuming the dimension for feed forward is 6, and the dimension for weight matrix for the first layer, 4 by 6. For the second layer, the weight matrix also 6 by 4. That's how we assume. So 4 rows by 6 columns, and the second layer, 6 rows by 4 columns. Now, here is the assumption of our weight matrix. So now we have 4 rows by 6 layers, 4 rows, 4 by 6, and bias as well. Uh, uh, one one array of bias for that weight matrix. And now we have also weight matrix 2, which is 4 by 6, and bias is 4, 1 by 4, 1 by 4. So now let's do first hidden layer, which is x multiplied by W1. That's x, first row of x. If I take you back, that's your first, which is I, for the word I, for the first token I. I like Rojava, that's second token. So we have this one, we multiplied by 6 columns. Okay, 6 columns. Now, so 6 columns, so 3 rows by 4, multiplied by 4 by 6. So 4 will, with 4, they go. The internal dimension, the only left is 3 by 6, the product of the multiplication of two matrices. Now, if we multiply 1.5 by 1 and 2.5 by 0, so that is, I show you, so multiply the first cell by this one and the second cell by this one, and so on and so forth. So we will find for the first column, that's the result. The second column, again, the first multiplied by the second. So 1 minus 1.51 multiplied by 0 plus uh, 1.28 multiplied by 1, and so on and so forth. Let's do it. So that's for the second one. It is done. Likewise, for the third column, we do it. And for the fourth column, we do it. For the fifth column, we do it. The same, the first row. That we are in the first token. First token, token 1. So first token. Now we found hidden layer for the first token, and it is, as you can see, it's 6 features. So it was 4 features, now we got it 6 features. So we multiply H1 by W2 now for the second, so that we can get H2, second hidden layer. H2 equals H1 multiplied by W2 and plus the bias. So H1, it's done. Now for the, no, sorry, we will follow the, sorry, here, because we have a relo. So we will, before it can be ready for, to, as an input for the second layer, we will subject the output into relo. Um, the activation function. So really what does it do? Negative will get to 0 and we'll get the X max of it. So here, any negative, so if it was, for example, any negative will get to 0, that's negative will get to 0, that stays at this. This is 0, this is 0, this is 0, and the rest will stay as it is. So that is 0, 0, and the rest will stay. For the same token, we'll do relo. And for the third token, we'll do relo. And now we have uh, row 1, row 2, row 3. So 3 tokens that we have, we multiply them by the weight matrix 2, which is 6 by 4. Now, because we received 3 by 6, the hidden 1, um, and in order to get multiplied by W2, so internal dimension will get removed. So if the product, we will get a 3 by 4. So we will get 3 by 4, 3 rows by 4. Now we have 4 for token 1. This value, 0 multiplied by 1, and that's the 1. If we go back, that is 1. And 1.5 multiplied by 0, that's 1.5 multiplied by 0, and so on and so forth. So that's how we get for column, sorry, that's how we get for column 1. For 1 and dimension 2, dimension 3, and 4. That's how we get it. That's for first token. And we do the same thing for the second token. For the second token, we do the same thing. So that's the input that we have. And we multiply it and we get the result. For token 3, for token 2, that's the result. And for token 3, likewise, we have each token row multiplied by each column of W matrix 2. So that is the results for feed forward neural network. So that's the final dimension. We'll have 3 by 4. So if we just go back to just double check, so that's the X that we have. We will have feed forward network, which is relo activation function, X multiplied by weight matrix 1 plus B. That will give us, this will give us H1, H1, and if we multiply it by W2, that would be H2. So H1 multiplied by W2 plus B2 will get H2. That's what we are doing. And now we have two weight matrices. That is the more or less the explanation how we can do feed forward network. Now, just to see whether if I missed anything, I think I explained everything in detail. Now, what happened? The first linear layer expanded representation, it was 4 features to 6 features. And the ReLU introduced nonlinearity. Second linear layer projected back to from 6 features to 4 features. And because the second linear layer, there wasn't any activation function. We just got the H1 multiplied by W2 plus B2. So that's two. So this is linear layer. That's just projected by from 6 features to 4 features. Okay. So what we can understand to describe the feed-forward neural network in Transformer is that the first linear layer expands representation when we multiply X by W1, we converted 4 features to 6 features, and the first layer increased to 6 features, which allows our model to have more space to learn different samples, different patterns. So if you have 4 features, for example, and change it to 6 features, it means that you are dealing with difficult, complex patterns. Now, really, what does it do? It keeps negative value to 0 and takes maximum of the positive values. And this is, again, it helps uh, the network, it helps the network learn uh, to deal with more complex relationships uh, instead of just uh, linear patterns. The second layer, which is the second hidden layer, um, brings back from 6 features that was done from the first layer, first hidden layer. So take it back to 4 features, and so that it can be aligned with the other layers of the transformer. For example, we need an output of the original dimension, and that's why we got 4 features. Um, why this operation is useful? Well, we said we will deal with transforming information from different features, from 4 to 6 and from 6 to 4. There was a nonlinearity ReLU, which deals with complex patterns and also higher representation power that we will have. So the tokens, they will have better representation, better understanding of each other. So this expansion of information will get better space, better learning, better dealing with complex features, and it again compress it back or make it compact so that we will keep the original size of the dimension so that it can go to the next layer of the transformer. That's all we have. The next part of our explanation, it will be about add and norm, layer norm, add residual and layer normalization. So if you have any concern or any question, there are links that you can follow. And if you need um, any answer or particular problem, drop me email. Thank you very much. Stay tuned for the next class. Thank you.